This is a slide that we've already seen, that the function, a function f is continuous if the limit as x approaches a is equal to the value of the function at a. Okay, so that's the definition for continuity. You're going to have to use that today, so it's good to know it. Okay, I'm just going to move this so I'm not like in the way. Okay, so a function, yeah, is continuous if it meets that requirement. And remember, at endpoints, the full limit doesn't have to exist, just the left or the right, depending on what side the endpoint's on. Okay, so that's the definition for continuity. Okay, so here, this is a really important theorem. It's called the intermediate value theorem. It's going to come up for sure on your test. It usually comes up on the exam and the AP exam. So just a super important theorem. And it's actually not a complicated theorem. It's pretty like intuitive. People just kind of have trouble, first of all, with the way it's written, because that's not necessarily great at reading mathematical sentences, but also they have trouble explaining it and remembering what it matches to, because later on in the course we learned something called the mean value theorem, and people just can't keep them straight even though they're not similar. So anyway, so the intermediate value theorem is a theorem that says that if a graph y equals f of x is continuous, so it has to be continuous, that's one of the things, on a closed interval a, b, and it takes on every value, then it takes on every value between f of a and f of b. Now all that's like really kind of obvious. What it's saying is that if a function starts at a value here, like down at the bottom, okay, like right there. Oh, I think my stylus is turned off. Just a sec. Yep. Okay, so down at the bottom of that graph, if you look at it, okay, right here, okay, if that's a f of a, that would be the coordinates for that point, right? A comma f of a, because f of a is just the y value at a. Okay, so that we could say it that way. We could say it's a f of a. Okay, all it's saying is that it starts at f of a and it ends at f of b, which obviously it would have to. That's how that coordinate there would be b f of b. Okay. Then it also must be every value, every y value between f of a and f of b. Okay, which makes sense. So let's do it with just something with some numbers. Okay, and then it says, in other words, if y naught is between f of a and f of b, then y naught is equal to f of c for some c and ab. And that's the actual definition. But let's just try this out and exactly what it means. Okay, so it means that if I told you that some continuous graph had a value at -1, 2, and a value at 3, 6. Okay, so what that means, right, is that there's some value like over here at -1, 2, and there's another one at 3 and 6. Then if I asked you, is there some point, and I told you it's a continuous graph, some point x equals c where f of c is 3, okay, what that means is there a place where the y value on this graph is 3, if the graph's continuous? Okay, now it has to be, because there's no way I could draw a continuous graph between these 2 points without going through 3. Like, I just can't do it. Like, I would have to jump, right? The only way I could draw this graph, I could go like down below like that. I could go up. I could go straight to it. I could squiggle around a lot, go up and, I mean, I can't do that because it's a function, but I could go like up, down, up, down, up, down. Yeah, I could do whatever I want, but at some point, it's going to have to pass through 3, because the lowest value is 2 and the highest value is 6. So somewhere in between, it must be 3. It's going to have to pass through 3. That's what the intermediate value theorem states, and it's like pretty intuitive. Okay, really, because there's just no way to draw a graph that wouldn't go through 3. So this theorem gets used, so the answer is yes. There would have to be. There has to be somewhere where the graph has a value of 3. So this gets used mostly to prove that graphs have zeros. That's what this mostly is used for. So if you can show that the graph is negative on one side and positive on the other side, well, it has to pass through 0 then. So it gets used to show that there's an x-intercept, is typically what it gets used to show. Okay, but let's see a couple examples. It's a pretty straightforward theorem, though, like I said. Does everyone kind of understand it? Does anyone have any questions? Yeah, so it's just saying, like, if it goes from this one went from 2 to 6 on the y-axis, then it must be 3, it must be 4, it must be 5, it must be 2.5, it must be 3.5, it must be every value between 2 and 6 somewhere. That's all it states. Okay, so let's look. Sometimes what you'll get is you'll get questions where the intermediate value theorem doesn't actually hold. So for instance, for this function that you have, the intermediate value theorem does not hold. Why not? Because it's not continuous. You just say it's not continuous. So that's one of the reasons that, actually that's like the main reason why the intermediate value theorem won't work. So for the intermediate value theorem to hold, the graph must be continuous. Since this one has a break, it doesn't hold. Like, if I just told you, and this is the thing, students get tricked a little bit, I think. Because if I didn't show you this picture, but I described this graph, and I said a function f of x, oops, that's crazy looking, f of x passes through 1, 0, and 4, 3. And if I told you that, okay, and I didn't say anything about it, like say you didn't even have this picture, that's true, because this goes through 1, 0, and 4, 3, and I said, so, at some point, will it have a y value of 2? And I asked you that on a test. And I didn't show you a picture, but I described that. Okay? I feel like a lot of people would say yes, because they would draw it out, and they'd be like, oh, well, if I'm going from 1, 0 to 4, 3, if I'm going from 1, 0 to 4, 3, okay, it must pass through 2. Okay, it has to, because I'm going to draw that function, and it's going to go through 2. But it doesn't say it's continuous. So this function, as far as I know, could just be these 2 points. Okay, that would be a function. 2 points would make up a function. So it's important to look for the word continuous when you're reading a problem like that. It would have to say a continuous function f of x passes through 1, 0, and 4, 3. And if it doesn't say that, like if it doesn't say the word continuous in a question, immediately I start thinking it's not continuous. Yeah, I'm like, what if the function wasn't continuous then? What would it look like? And I could draw a function however I wanted here. Like I could draw something like that or whatever. That's kind of what this one looks like. And I have this hole in the middle where it doesn't pass through those values. Okay, so that's why it doesn't hold. So always ask yourself, if you're trying to use the intermediate value theorem, if the function's continuous, and if it's you can't use the theorem. Okay, so here's another one. Use the intermediate value theorem to show that there's a real number that is exactly 1 less than its cube. And I imagine this would cause panic on a test because students wouldn't know what to do with it. Okay, so it's telling me there's a real number, so let's call it x. Okay, and it says x is means equals, exactly 1 less than its cube. So how would I write 1 less than its cube down? Yeah. All I want to prove is that there's some number that would make that work. Okay? So using the intermediate value theorem, what I would probably do is I would get one side equal to 0. Oops. So I get 0 equals x cubed minus x minus 1. Okay. Now, if I plug 1 into this, so if I let x equal 1, okay, imagine this is a function here. What do I get? What do I get there? That equals -1. Okay? Now, if I let x be, let's just say 2. Oh, yeah, okay, let's just say 2. What do I get for the y value? Or what do I get when I plug it in there? 5. Thank you. Okay, so the fact that this graph, which would be a continuous graph, because what type of graph is that? It's cubic. And cubic graphs, like all polynomial graphs, are continuous. So my graph is clearly continuous. And at 1, I get -1, and at 2, I get 5. That means that my graph has to go from 1, -1, to 2, 5. And it's continuous. So somewhere between 1 and 2, it has to have a 0. So somewhere between 1 and 2, there is an answer that works. Okay, that's what we're stating here. So I'd say, okay, my answer would look something like, I'd write something along the lines of, by the intermediate value theorem, there must be a value for x that works in the interval 1, 2. Okay? That's all I'd say. Okay, so since I see one value that's negative, one value that's positive, there must be a 0 in between them. That's usually what the intermediate value theorem is used to prove, is that there would be a 0 somewhere. I'm assuming some people are wondering how I came up with these numbers, the 1 and the 2. I just picked them randomly. I thought, how could I make that negative? That's what I thought in my head. I just did it. I haven't looked at this problem in about a year now. And I looked at it, x cubed minus x minus 1, and thought, how could I make it negative? And I thought 1 would work. And then I thought, how could I make it positive? And I thought 2 would work. And then I plugged them both in. Okay, so it's not like I'm not doing any crazy math. You could pick other numbers. If I put 3 in, it would also give me a positive. And then I could use that value instead. Okay, so it's just a matter of picking. Generally speaking, you will be given those two x values. It will say, is there a 0 on the interval 3, 5? Then you know you have to plug in 3 and you have to plug in 5. Okay, so that's usually how. Okay, so one more here. This is, like this. This is the typical IVT problem. Okay, so they give us a function, p of x, 2x cubed minus 5x squared minus 10x plus 5. Is that continuous? Yes, it's just a polynomial function, so it's continuous. And it says, prove that it has a root somewhere in the interval -1, 2. Okay, so there's some 0 between -1 and 2. So first, okay, I would say, if I was actually showing it, I would say p of x is continuous. So the IVT holds. Okay, you should make note of that. If you're really doing good math, you would make note of that to say, hey, this theorem, I meet the qualifications for it. Okay, so I'm allowed to use it. Okay, then what you do is you find p of -1. So p of -1, if I plug it in, 2 times -1 cubed minus 5 times -1 squared minus 10 times -1 plus 5. Okay, that's -2 minus 5 plus 10 plus 5. So it's 8. Okay, and I do the same thing. I find p of, I find p of 2. So I do the same thing, but with 2. So 2 times 2 cubed minus 5 times 2 squared minus 10 times 2 plus 5, okay, which is 16 minus 20 minus 20 plus 5, and I can clearly see that's negative even without knowing the exact value right away. Okay, so I have 21 minus 40 is negative 19. Okay, so the actual like nice sentence you would probably write about this is since p of negative 1 is greater than 0 and p of 2 is less than 0, there must be some value x equals c where f of c equals 0 by the IVT. Okay, that would be like a very nice sentence. Okay, that is like a perfect mathematically phrased sentence where I'm saying since the one value is positive and the other value is negative, there has to be a value, and I give it a name, c. There has to be some place c in between them where f of c equals 0. Actually, to be even more precise, there must be some value x equals c where c is in A, B. It must be between A and B. Okay? That makes sense? Okay, so that value of C must be between A and B. That's even more precise. Just saying, basically what you're saying is I know there's a 0 between negative 1 and 2. Okay, and you could write that instead. There's more than one right way. It doesn't have to be identical to this, but you'll see this language used a lot in IVT problems where they say, is there a value C such that? Okay, and they'll phrase it this way. So getting you used to seeing that is an important thing. So this is just a theorem. Theorems are things in math that somebody has proven. We could show you the proof. Like somebody had to prove this thing, which you look at a thing like the IVT and it's like, yeah, obviously. Like it seems like that should be the proof. It's like you ask everyone and everyone's like, yes, that just seems to make sense. But somebody had to prove it rigorously. I bet you it wasn't pretty. It's a lot of work to prove things like that. So someone has proved it, and now we all just use it. Okay, we're like, someone's already proven that. We can just assume it's true, and now we use it to show things. Okay, that's what theorems are all about. So if anyone's like interested in doing a math degree, that's what mathematicians do, is they prove things like that. Okay. I have a good friend who did his doctorate in math. And his doctorate, his thesis was, there was like a bunch of mathematicians working on this huge proof, like this huge thing, like it was like a book, like they were working on a book, and they had one line in it, and they said, in the next 4 years, you need to prove that one line, and that was his job, and he spent 4 years on it. And he did it, so he got his PhD, okay?